15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts. My name's Andrew Dunkley, your host, and with me, as always, Fred Watson from the Australian Astronomical Observatory. Hello, Fred.
Hi, Andrew. How are you going?
Oh, good. I just wanted to make it sound more significant, what you do.
Well, it certainly is. Yes, putting a pause in between each word certainly emphasises the gravitas of what we do.
Indeed. And speaking of which, we are going to be talking about gravitational waves today because they've detected a new batch of them, and it's got something to do with merging black holes. We're also going to look at the results of NASA's Juno spacecraft, which is orbiting Jupiter, some information there. And the question today comes from Dave at Shawnee, who is not the Dave, it is the Dave we were talking about last week. But we've finally caught up to you, Dave, so we'll have your question answered with aplomb very, very soon. But first, Fred, these gravitational waves. Now, people are probably still trying to get their heads around these things because they're only a fairly recent discovery in the scheme of things, and they are a telltale sign of something that has escaped my mind. So you tell me.
I will tell you, but let me preface our conversation about this, Andrew, with news that's just come in today. So as we're recording this podcast, we've just heard that 3 of the scientists who were key to the original detection of gravitational waves a couple of years ago by the LIGO experiment, and we'll talk a little bit about that in a minute, Rainer Weiss, Barry Parish and Kip Thorne Rainer is from MIT, the other guys are from Caltech. They have been awarded the Nobel Prize for Physics in 2017. It's not a surprise, but it's very good news.
It is indeed, and not surprisingly, and how they're going to split the $10.
I'm sure they'll work that one out.
Yeah.
But no, that's great. That is great news. So, all right, what are gravitational waves? Well, they were predicted by Albert Einstein over 100 years ago in his general theory of relativity. Because what Einstein said in that theory is that space can kind of bend, that space itself has a sort of flexibility, although it is actually really very rigid, but it is on large scales is flexible, and that's how what we feel, the way we feel that flexibility is as a gravity. So the force that's keeping you in your seat and me in my seat at the moment is not actually a force as Newton said it was. It's a slight distortion of the space around the Earth because the Earth is a massive object. So that's setting the scene. But what Einstein said was, well, if you've got a bendability of space, anything that can flex or bend can transmit waves through it, like the air transmits sound waves because air can bend, or can flex. So that is basically the origin of gravitational waves, and what causes them is something big being accelerated. If you accelerate a large mass, then it will stir up the space around it to emit gravitational waves, and they travel through the universe at the speed of light. So you might remember that at the beginning of last year we had the announcement of the gravitational waves detected in America by 2 basically laser devices that kind of 4 kilometers square. They're very big. They are situated at different points in the United States. They registered the sort of shuddering of space as this wave went through, and you can get a rough idea of the direction by timing the difference between it hitting one of these LIGO detectors and the other. It doesn't give you particularly good direction, but it gives you at least an idea of whether it's the northern or southern hemisphere. And what was basically being detected then was the merger of 2 black holes. So 2 black holes coming together in space, they spiral around one another. And in about the last half a second or so, they're spiraling so rapidly that they really shake up the space around them. And we, something like 2 billion light years away, can eventually, 2 billion years later, we detect the incoming signal from that stir up. It's just like throwing a stone into a pond, and you wait for the ripples to get to the edge. So the disturbance is the stone dropping into the pond, and the gravitational waves are what we see sometime later. In this case, a couple of billion light years. So why is it in the news? Well, they have now detected another one, and in fact, it's not the second. There have been 4 so far. The original one. Actually, the event occurred on the 14th of September 2015. One followed it on Boxing Day 2015, and then January I beg your pardon, there was one in October as well, 2015. Then one in January this year, and now we've got a new one on the detected on the 8th of August this year. But there's a big difference, and that's why this is exciting. Can you guess what it is, Andrew?
Something to do with black holes merging?
It is. Well, it's actually the phenomenon is much the same. This event was 2 black holes about 1.8 billion light years away. Their respective masses were 31 and 25 times that of the sun. They come together to form something actually 53 times the mass of the sun, which means 3 times the mass of the sun disappears, and that goes into the energy of the gravitational wave. But what's new about it, Andrew, is the way it's been detected, because there is now a third a laser detector in the world, which is up and running. It's been under construction for some time. It is called Virgo, and I can't remember what Virgo. It might not even be an acronym. It might just be a name. It's near Pisa in Italy. And so what you now have is 2 LIGOs, these laser detectors, the American ones, separated by several thousand kilometers, but another one in Italy separated by even more thousand kilometers. And having 3 allows you to triangulate the direction from which these gravitational waves have come. So effectively, you're building a telescope. You're starting to build a big gravitational wave telescope to pinpoint where in the sky they emerge.
That's astounding. And I suppose what we're learning from this is, the more technology we put into it, the more common these things seem to be.
Yeah, that's the big surprise, I think. Everybody kind of expected that what we will be seeing will be mergers of neutron stars, which are a less energetic thing than mergers of black holes. But so far, the first 4 events that have been detected have all been due to black holes merging. And it's not kind of that unexpected, because we know the universe is full of black holes. And remember, we're able to see these things at distances of billions of light years with these detectors. So that's a huge volume of space, probably many billions of galaxies actually within that volume. And they have their own black holes, what we call stellar mass black holes, which are the ones that have been detected so far, as well as, of course, their huge black holes at the centers of their galaxies. So merging black holes is going to become a real, I suppose, production line in learning about the universe and the history of the black holes. But as I said, once again, to emphasize, the new thing with this is the fact that adding the Virgo detector into the mix allows you to pinpoint where these signals come from to a much better accuracy. It's still only an area 3 times the size of the full moon. So it's not microscopic imaging, but it's better than just half the sky, which is kind of what we had before. Yeah. So I think this is a remarkable step forward, and congratulate all the people involved, particularly the ones who've just received their Nobel Prize or been designated as receiving the Nobel Prize today. It's great news.
They can take their certificate, fold it up, put it in a drawer, just like everybody else. Yeah. Awesome.
That tends to not to be where Nobel Prizes.
I kind of suspected that. And just as a side note, I don't know if you completely answered this, but what does happen to 2 black holes when they smash into each other? Do they obliterate each other or become one big black hole?
No, that's right. They become one big one. They go through. It's really interesting. So they spin together. They don't just collide. They actually approach one another sort of obliquely. And sometimes that approach might take millions of years, but it's the last fraction of a second when they're rapidly spinning around one another that they're really stirring up the gravitational environment. What happens then is they come together. There is something called the ring down, and that's when they actually have collided, but the black hole itself is sort of vibrating, or the event horizon is, and then settle down to being a merged black hole. But as I said, the merged black hole actually has a smaller mass than the two coming together. And you lose 3 times the mass of the sun in this process. And that is what, with the famous equation E equals mc squared, the energy of that mass turning into gravitational waves is what we detect with these machines.
Glad I asked. All right.
I'm glad you asked as well.
There'll obviously be more to come on gravitational waves and merging black holes into the future as we get more and more capable of detecting these things, and who knows what we might learn.
Exactly. That's the great. Sorry to interrupt you, Andrew.
No, but that's
the great thing. What we've done is opened up a whole new window on the universe with this, and that's why it's so exciting.
Indeed. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, we're going to revisit an old friend. That is the tiny little world that we know of as Jupiter. And we're going to focus on the Juno spacecraft. All the talk recently has been about Cassini splashing down in Saturn, so to speak. But in the background, Juno's been doing its thing. What's the latest?
That's right, Andrew. Yes, Juno arrived in the vicinity of Jupiter rather more than a year ago now. So I think it was July last year. And so it's been going through its mission. It's in orbit around Jupiter. It flies over the poles of Jupiter in a very elongated orbit. And the idea of that elongated orbit is to try and keep the spacecraft as far as possible out of Jupiter's radiation belts, which arise because of Jupiter's intense magnetic field. So we've got lots and lots of new information, and they've come from a special issue, I think, of Geophysical Research Letters, which has 44 papers coming from the Juno mission, as well as a couple of studies that have come from the Science Journal. So lots and lots of stuff floating around now, revealing the details of what we've found. And there's a bit of a list here. So just going through it quickly. First of all, around Jupiter's North Pole is totally different from Saturn's. You and I have discussed Saturn's North Pole before, which has a strong high-speed vortex at the center, and then this enormous hexagonal jet stream around.
Yeah, that's right.
Perfect hexagon. Looks as though you should be putting a spanner on it rather than observing it on a planet. Jupiter is nothing like that. It's just turbulent, an absolutely tumultuous area, oval-shaped cyclones, which are, they're huge. They're 1,200 kilometers across or something like that. So a very, very different regime near the North Pole of Jupiter from what we get in Saturn. And, that's a really quite hard thing to understand, because we think these two gas giants are rather similar in their structure, but apparently not, certainly not in their upper atmosphere. And then the one that I think is really baffling, one of the things that we have sort of hoped with the Juno mission is that by observing the way the planet distorts the orbit of Juno, we might be able to plot kind of what's going on underneath Jupiter's clouds, what's a sort of a world we're looking at. And there was always this thought that right at the center of Jupiter there will be a solid core, that because it's a gas giant, that doesn't preclude a solid core. And in fact, people have speculated that it may be something called metallic hydrogen, whose existence we do know, but we've never really seen it en masse. But it's really apparently not like that at all. The thinking now is that there is no distinct core. There's no place where you can say, 60,000 kilometers below the surface, it changes into a solid object. Apparently, it's not like that. There's a comment here from one of the scientists we used to think that there was a little ball of heavy elements, small and quite distinct at the center. Now we're thinking that that mass may be much more spread out. Maybe there was an original rocky ice core in the bottom, but it's being dissolved away because of the heat and the pressure. And maybe there isn't a liquid metal hydrogen core at the middle that is sharply differentiated from everything else. So a real question about what the inside is like.
Yeah. Well,
yeah.
I suppose the difficult question to answer is how do we really find out?
Probably other missions that people will cleverly put together to analyse that sort of thing. But Juno really is the best we've got at the moment.
It must be really frustrating, Fred, for them to launch a mission like Juno, get the equipment the way they want it, then go there and learn something that spacecraft is incapable of elaborating about.
Exactly.
Knowing full well that it's going to cost millions and millions of dollars and months and years to then send another spacecraft to find out the answer to the questions that have evolved.
It's really remarkable. Just moving on, there are questions that have been answered. The atmosphere of Jupiter apparently has similarities with the atmosphere of the Earth. On the Earth, we know that in the equatorial regions, you get these what are called Hadley cells. There's a thing called Hadley circulation. It dates back to a 17th century astronomer, actually. And so winds blow in towards the equator. They kind of rise up and generate thunderstorms. And then the winds flow back towards the poles. There's this circulation in Jupiter's atmosphere. This is similar apparently on Jupiter, much bigger cells, of course. And there's a comment here, instead of water, they rain out ammonia crystals that quickly evaporate. We know there's a lot of ammonia in Jupiter's atmosphere, but it's a surprise that it actually rains crystals in Jupiter's atmosphere.
Wow.
And just moving on, the magnetic field's twice as strong as we thought it was. It's about 10 times stronger than the Earth. But perhaps finally, and one of the really interesting things, of course, the magnetic field is driven, as the Earth's is, by what we call dynamo effects. It's circulation of essentially metallic or stuff that conducts electricity being circulated in a planet. In the case of the Earth, it's our iron core that causes the dynamo that gives rise to the Earth's magnetic field. But Jupiter's is really complicated, and apparently it's quite high up in the atmosphere of Jupiter, which means that the thinking there is that because Juno has seen very strong sort of small-scale variations in Jupiter's magnetic field, that might be what gives rise to the magnetic field overall. So we might be seeing the sort of granularity in structures near the surface of Jupiter that are giving rise to the magnetic field. Remarkable stuff.
Well, if it doesn't have a core, you can't say the core is the cause.
That's exactly right. That's right.
So there must be something else going on.
Lots going on, and it's up to us to find out what it is, Andrew.
And how long will Juno be in operation?
I think it's got another year or so. It's got a specific number of orbits, and then, of course, it will be plunged into the atmosphere of Jupiter, just like Cassini was, to avoid any kind of contamination of its moons.
Okay, which is what the question is about today, in fact. So we'll get onto that shortly. But the Juno mission, the Cassini mission, they're sort of mapping out where we go next as far as exploration of the gas giants and the outer solar system is concerned. We've really achieved a lot in recent years when you think about it. Pluto and so many other things. There's been some astonishing revelations, really, Fred.
We're not doing badly, are we? And thanks largely to NASA, who run on a budget that really is, I think their budget should be doubled. It's not that adequate.
Yeah. Just like most government organisations, though, they suffer the wrath of the knife from time to time, which makes it difficult. But I think they're pretty amazing. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Right, Fred, to another listener question. We love your questions, by the way, so keep them coming. You can send them to us via Twitter, via bitesz.com, that's bitesz.com, where our podcast originates, actually. Or you can jump on our Facebook page and send us questions there. I do check them once a year. Now, this comes from Dave in Shawnee, Kansas. Thank you, Dave. We were mixed up with you and another bloke last week, but we finally nailed you down. Now, he says we apparently had no worries about nasty old microbes when sending a lander to Titan, but killed off Cassini because it might contaminate Enceladus. Why did we play favourites?
It's a great question, and it's similar to one that I've actually asked a couple of times to people who ought to know, including one astronaut. So let's just review what this is about. We sent a lander to Titan. We did. Back in 2005, the Huygens probe landed on the surface of Titan. It did a soft touchdown. It worked for a number of hours before its batteries ran out, and sent back some images of the surface of Titan at a temperature of minus 180 Celsius, which is the surface temperature there. So why weren't we worried about microbes being carried from Earth to Titan? Well, we were, because every time you send a spacecraft to the surface of another world, you have to go through this what are called the planetary protection rules, and that specifies what level of sterilization, biological sterilization, it needs to receive because of the risk of infecting another world with earthly microbes. So that basically that process would have happened for the Huygens probe, which is relatively small, kind of size of a fridge, more or less. The main spacecraft itself, though, Cassini, is much, much bigger than that. It was about 7 meters long. It's a colossal thing. So would have carried a much higher burden, as they call it, of spores, of microbial spores, just because of the size. Even though it was also sterilized, you've got a much bigger risk with the Cassini spacecraft. Plus the fact that had they let Cassini just run out of fuel, it would have been basically uncontrolled, orbiting the planet Saturn, and may well have wound up colliding with Enceladus or Titan or one of the other moons of Saturn, which would have been a bad thing, potentially contaminating these worlds. So that's why we played favourites. It's really just to play as safely as we could. But of course, the same question arises with Mars. When you send a rover to Mars, you have to sterilize it to a very high level, particularly if it's going to somewhere where we think liquid water could exist on the surface of Mars. There are a few places that occasionally reach temperatures above zero. So you have to deal with all that. But here we are talking about sending humans to Mars down the track, and of course we're certainly not sterile in that regard. And so there has to be the question, well, how do we deal with that? And the answer I got from the astronaut I asked a couple of weeks ago, Sandy Magnus, who was visiting Sydney, she said, look, they will basically modify the rules to suit. So there's going to be clearly a pragmatic approach to this. Eventually, we will be sending humans to Mars, and humans are full of microbes. We can't do anything about that. We've just got to live with it and maybe ensure that the contamination is minimized on the surface of the planet.
How human is that? Look, the rules are this, but when we go there,
exactly.
We're going to change the rules.
We'll change the rules. That's exactly
it's like the America's Cup. Sorry, but...
Yeah, exactly. So there you go. Thank you very much for that, Dave. That's a great question.
It is a brilliant question. Yeah. But look, it does make me think that early on we didn't consider any of this sort of stuff. So we were sending probes all over the place, Venus, Mars, the moon, et cetera, et cetera. And they were smashing into it and exploding all over the place, and dropping their lens caps and all this sort of weird stuff.
Yes, that's right.
Surely the damage is done. Surely. I don't know. But look, thank you, Dave. We do appreciate the question. Hope we did answer it for you. Dave was also very intrigued by your comments regarding the risk faced by an astronaut who gets water in his helmet. Apparently, this is something that other people have been discussing in the podcasting sphere. But do you want to elaborate on why water in a helmet's a bad thing in space?
Just because it collects into globules, and of course, it's not just swirling around in the bottom of the space helmet. It's surrounding you, and a little globule of water going down into your lungs is a bad thing.
Yes, indeed. And there's nowhere to run after that, really.
That's right.
Unfortunately.
Exactly.
Okay. Fred, thank you as always. Great to talk to you.
Great to talk to you too, Andrew, and I look forward to talking again very, very soon.
Yeah, that should be fantastic. Fred Watson from the Australian Astronomical Observatory. He is one half of Space Nuts. He's in his pod, I'm in mine. And apologies for a bit of sound quality issue. We certainly have had some fun with the internet during this occasion, but that's the way it goes, and we do appreciate your patience. But don't forget the feedback. Send us notes, send us questions, send us ideas. If there's something you think we should be talking about, we don't want to know, but you can send us the question anyway. We'd love to hear from you. We'll see if we can sort it out. Until next time, thank you as always for listening to Space Nuts.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.